In this chapter, we learn generalized estimating equation, GEE. And here I say analysis of repeatedly measured binary categorical variables. Although GEE you can use for many different types of outcome variables. And GEE you can find in SPSS right under generalized linear model. Okay, and what GEE does is it the repeated measured capability to generalize linear model. And these are the regression and you can do in generalized linear model, which include linear regression, ordinal logistic regression, binary logistic and Poisson regression, negative binomial regression, which is similar to Poisson regression. And there are more regressions you can do with a generalized linear model. And so GEE adds repeated measures aspect to this regression, which means and you can analyze any of these regressions where data have repeated measures. Okay. And GEE is the most flexible model among the regressions we have learned so far in this class. So this is an example from a literature. And this studied change in the pain score and over time. So as you see, the pain score is a continuous variable. And they showed how the pain score changed over time among 4 groups of patients. You could use a mixed effect model for this analysis, and or you could use a GEE. Okay, so they say they used generalized estimating equation in GEE, and they actually mistakenly spelled as a generalized estimated equation, which is actually wrong, and you have to say generalized estimating equation. So what we do today is, as a first example, and we are going to analyze dental growth measures data, and we compare rate of change, annual rate of change between boys and girls. We did do this analysis using mixed effect model in the previous chapter. Okay? And although today we are going to use GEE, okay? But we actually will do the same thing, but use different regression. You go to analyze generalized linear models, and under generalized linear model you find the GEE. Okay? And this is the first screenshot in GEE. So similar to mixed effect model, you put the ID under subject variables, and then you put the age under within subject variables. And GEE does not have a random effect. Okay, so no random effect. And although it has a correlation structure type, so this part is similar to first screen we saw in the mixed effect model, and asking what type of covariance structure and you want to use. So here, mixed effect model is a covariance type, but GEE is a working coordination matrix. It's basically the same thing. Okay? And if you click on that, and these, there are 5 types of correlation structures, which is much less compared to mixed effect model. Mixed effect model have about 15 different types of correlation structures. And independent is the same as scaled identity in the mixed effect model. Okay? And this simply doesn't assume any correlation between repeated measures. And AR1 is a first order regressive, which is the same as mixed effect model. And exchangeable means compound symmetry in the mixed effect model. And unstructured is the same as unstructured in a mixed effect model. And M-dependent is similar to toplets. And do you remember toplets? Toplets, okay, diagonal elements would be 1. And then correlation between measurement 1 and the measurement 2 would be 8A, and correlation between measurement 2 and measurement 3 would be also A, and measurement 3 and measurement 4 be A. So here it's the same, A. And then here, correlation between M1 and M3 will be B, and M2 and M4 will be B, and M3 and M5 will be B. It's the same. And the M dependent, actually this assume correlation becomes 0 and after some lag time. Yeah. So that's the difference between toplets and M dependent. And GEE in SPSS have these 5 different correlation metrics. Okay. And this analysis and outcome variable is a dental growth measurement, and which is a continuous variable. So you click linear, because without the repeat, and we would use a linear regression. And then a response screen, and you put the growth dependent variable under dependent box. Okay? And then move to predictors. And predictors, and we are going to analyze difference in rate of change between boys and girls. So we do need sex, and we need age, and we specify interaction under the next box. Okay? And sex is a categorical variable, so you put under factor, and when you put under factors, and let's click on descending. Okay, so you click options, and this box appear. So you click on descending, which means female, which is female, coded 0, reference category. Female would be reference category. So you're comparing male reference to female, right? And the age is a continuous variable, so you put under covariate. In the model, we need to put the main effect of sex and age and cross product term between sex and age. So model parameterization is exactly the same as what we did in a mixed effect model, right? So that's all you do, and then you click OK or Run, and this is the output and you have. And interpretation is exactly the same as what we did in the mixed effect model. So beta coefficient for the interaction, okay? And this indicate change in two slopes between boys and girls. So what does it mean? Okay. So main effect beta coefficient for main effective age. This is the slope of a girl. So 0.490 would be this. Okay. So this beta slope is 0.490. And then beta coefficient slope for boy would be 0.490 plus 0.294, which is 0.784. Okay, so this is the slope for boys. So then what is the beta for the interaction, which is this one, right? So this indicates difference between two slopes. So interpretation is exactly the same as what we learned in mixed effect model and also in a linear regression. So if this p-value is significant, then we know there is a significant interaction, and i.e. Two slopes are statistically different. And these beta coefficients are the same as what we obtained in a mixed effect model. However, p-value is slightly different because computation we use GEE is a little bit different from what they use in a mixed effect model. Okay, so it's easy, and we are done with the continuous outcome variables. And next example, which is the last example in this chapter, and we are going to use binary outcome variables. And RESP.SAV contains data from RCT. Patients in each of two centers are randomly assigned to groups receiving active treatment or a placebo. During a treatment, respiratory status, coded here 0 as poor and 1 as good, was determined for each of 4 visits. The variables center, treatment, sex, and baseline are binary categorical variables. And the variable age is a continuous variable. We want to assess the effect of the active treatment on the respiratory status. So if we go back to the data set, okay, and so this person, and this person, this is the baseline measurement. So this person has a poor respiratory status at the baseline. And visit 1, and this person still have a poor outcome, poor. Okay, and then ID number 4 person, say this person, and this person has a good respiratory status at the baseline, and visit 1, this person had good, and the second visit good, and third visit good. The fourth visit and outcome become a poor status on the respiratory function. Okay, so this is the data we have. So at the baseline, and you have a similar percent of a patient and who has good respiratory status between two groups. Placebo is blue and green is active treatment. Okay. And so we can guess randomization worked. And first visit, and you have a higher percent of patient with good respiratory status with active treatment, and less number of people with a good status with placebo, and that gives odds ratio of 2.25. So odds of having a good outcome is 2.25 times larger with active treatment at the visit 1. And visit 2, odds ratio became 3.778, so the difference became greater. And visit 3, odds ratio 3.1, and visit 4, an odds ratio of 2.01. Okay, and let me show you how to compute odds ratio at each visit. Okay, and we are going to split the data by each visit. By splitting data, and we are getting rid of repeated nature from a data, right? Because a visit 1 contains only data from first visit, so you don't have to worry about using repeated measures. So what we do is we split the file based on visit number and then run the logistic regression, and that will compute this odds ratio. And if you want to put the p-value in, yes, you can get the p-value from the logistic regression. So first you split the data by visit, and then perform binary logistic regression, not the GEE in this case, because within each splitted data and there is no repeat. And so you put the follow-up respiratory function outcome as a dependent and treatment. So covariate, and let's specify categorical box, and we want the first category to be a reference, and okay, right? So this is how I computed visit specific odds ratio of a treatment on the improvement of a respiratory function. And so what we want to do next is, instead of computing each different odds ratio, and we want to pull these 4 odds ratio, because when you show 4 different odds ratios and then multiple comparison could become an issue, and also readers of your paper might get confused with having too many different effects. Okay, so when you eyeball this, and then if you judge there is not much difference, and you are okay to pull, and then we can unsplit the data, and then let's pull these odds ratio. How can we pull? That means we adjust visit and then get the visit adjusted odds ratio of a treatment. So to do that, and now we are utilizing entire data set, so there is a repeat, and we can no longer use binary logistic regression. So we go to GEE now, and put the ID under subject and visit under within subject variables, and here, and we and in fact in GEE, when you have no missing data and every single patients have the same number of observation, in this case if everybody have a measurements on all 4 visit, and then choice of correlation structure doesn't really matter. In GEE actually do have iteration in computation. So even when you guess initial correlation matrix as an independent, by iterating this process, and GEE will converge to a right correlation structure. This is the difference between GEE and a mixed effect model. Mixed effect model uses a closed formula. So if you guess wrong correlation structure, and that will impact on the p-value. And although in GEE, as long as you have a balanced data, that means everyone had the same number of observations. If everybody have 4 visit data, and then you have a balanced and no missing data. And in this case, okay, whichever correlation structure you use, a model will converge to a right correlation structure. But when you have a missing or unbalanced number of observations between patient, and then GEE can bias the result. Okay, so in that case, it's better to start with the correct correlation structure. And so let's go back. Okay, and here, right, outcome is a binary. So you click on binary logistic, and response is a response follow-up. And here, this box got highlighted. So you click on reference category, and it's important to make this to the first choice. And otherwise, your odds ratio would be reversed. So click on first and continue. And predictor, and now, and we put the visit under factors. So we first consider visit as a categorical variable, and the treatment, and also under factor. And then here we need to specify descending order. And in this case, the treatment 0 would be a reference category, and so as visit 1 being a reference category. And then go to model. Under the model, you put the treatment and visit, and skip estimation, go to statistics, and let's click on include exponential parameter estimate. So this way, you don't have to use the calculator to exponentiate beta coefficient to convert to odds ratio. Okay, and then I think we are ready to click OK. And this odds ratio 2.688 is a pooled odds ratio of effective treatment and over 4 visit. And this is crude odds ratio. So if you get rid of a visit from the model, and this would be a predicted value based on this model, and as you see here, you see flat. So there's really no difference made by visit. And then this odds ratio and the model estimate being 2.679. Okay. And on the other hand, and if you put the visit in the model, and model actually do recognize differential effect by each visit, like second visit, and you have a smaller number of good respiratory function for both active and placebo groups. And then visit 1 and visit 3, and you have more patient with a good respiratory function. Okay, and although odds ratios are estimated being the same, so this odds ratio is 2.688. Okay, so you see similar difference here, 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 and here. And next, so let's see what happens if you include interaction effect here, right? And by including interaction, model become very messy. But what I want you to know is, and here, odds ratios are actually estimated differently. Okay, and it's really hard to explain this beta coefficient, but let's see, let's try. Okay, and so we get the gigantic model, so let's try to interpret this. And odds ratio of 2.254 is odds ratio of treatment where visit is a reference category. So this means odds ratio of 2.254. Okay, and then so here, okay, if you multiply these two odds ratios, and that would be an odds ratio of a visit 2. So this is odds ratio of a treatment, and which is 2.254 times 1.676. Okay, and then if you multiply this with this, and that gives odds ratio of treatment for visit 3. And if you multiply this with this, and that gives odds ratio of treatment at the visit 4. Okay, so by including an interaction term, and a model is capable of estimating odds ratio differently for each visit. Okay. And right, and so the p-value for these interaction terms actually assess whether the two odds ratios are different or not. So this p-value, let's see, this p-value is assessing this odds ratio, and this odds ratio is the same or not. And then this is assessing this odds ratio to this odds ratio, if these two are same or not. And this odds ratio is assessing, this p-value is assessing whether these odds ratio visit 1 and visit 2 are same or not. And now, alright, what's next? So what happens if you put visit under covariate? Okay. So if you put the visit under covariate, you see the straight line here, and then straight line here. It's not quite parallel. Okay, so effective visit, instead of recognizing as up down, and if you, so this is a model, you put the visit as a factor. Okay, so this sign means it says confidence interval around the mean, so you know you're comparing the mean. That means you're treating visit as a factor. And here you're treating visit as a continuous variable, so you put the straight line. So the model is not really capable of modeling effective visit as up down, but you just plot straight line here. Okay. And so let's try to explain odds ratio. So odds ratio of a treatment is, so this one, and this means odds ratio of treatment where visit is 0. So in this case there is no visit, which is 0. So here this odds ratio is actually larger than odds ratio in here. Okay, actual odds ratio is 2.25 and 1, right? But so this odds ratio is not really visit 1, it's at the visit 0, so slightly larger than odds ratios at any visit. And then and this p-value indicate whether the odds ratios are modified by visit. Yeah. So as you see, these two lines are nearly parallel. It's not quite parallel, but it's nearly parallel, and therefore so this model did not detect the interaction between the treatment and visit. But again, there is a big assumption of this model is effective visit is a linear. Okay. So here the point of this exercise is I wanted to see the impact or consequences of changing parameters by putting visit as a factor or visit as a covariate, and also including interaction or not including interaction. And this parameterization, SPSS does not really tell you what to do. So you really have to think how to treat time variable, whether you want to put it as a categorical or put it as a continuous, because that will impact on the result of your analysis and also interpretation of your analysis. This is the last slide, and I'm trying to give you the quick comparison between different method. So the method, I put the GEE and mixed effect, and then random repeated measures ANOVA. I call it RANOVA method. So let's see, type of outcome variable. In RANOVA and mixed effect model only use continuous, but for GEE, and you can use continuous, ordinal binary counts, skewed continuous, and non-skewed continuous outcome variables. Okay. And GEE and mixed effect model, and the model utilize longitudinally formatted data, so you can let a value of covariate change over time. Okay. In RANOVA, now you have the model require horizontally enter data, so it can take only one value for each covariate, so it can't do time varying covariate. Okay. And so this column is actually the same as here. So the model which require longitudinal format, and you don't have to delete entire patient data when at least one observation is missing among the repeatedly measured outcome. But RANOVA is a horizontally entered data, so if one observation is missing, an entire row of data would be deleted. So entire data for the patient would be deleted. In GEE and mixed effect model, since it takes longitudinally formatted data, so it does accommodate differential numbers of observation between patients. So one patient can have just one observation, and some patient could have 100 observations. That's okay. In RANOVA, it requires horizontally entered data, so number of repeated measures within patient have to be the same for the entire cohort. Okay, and okay, so therefore RANOVA, and if you have a missing, and you can't include that patient data, so it doesn't accommodate missing observation. And a GEE and mixed effect, and yes, and you could have a missing observation, but the mixed effect assume missing at random, and GEE assume missing completely at random, so mixed effect is more robust for missing data. And here, okay, in GEE and mixed effect model, and let's say if the first repeat is happen after 1 month, and then second repeated measure happen after 3 months, and then third repeated measure happen after another year, and unequal spacing between visit is okay for GEE and mixed effect. And RANOVA model have no capability of considering a differential interval, and so it would be no. Okay. And mixed effect is good for small size sample size data, and so as repeated measures ANOVA, but GEE is not, and it's good for larger size data. Okay. And GEE, good thing about GEE is if you specify wrong coordination structure, independent structure, and the model will converge to the right coordination structure if you don't have a missing data, or if you have equal number of observations between patients. And mixed effect model, and if you specify wrong coordination structure, and then it can bias the p-value. And RANOVA, it only handles compound symmetry, so RANOVA is not flexible for a coordination structure at all. And random effect and mixed effect can handle random effect, and so but the GEE and RANOVA don't. And if your purpose is predicting a value for a particular patient, and then mixed effect is a good choice, because having a random effect, and you can estimate each patient profile. So I hope this quick summary help you to compare the difference over 3 methods.